The second problem is having multiple people edit the same code while ensuring that everyone can trust the history of those edits. That's where Git comes in. What Git actually manages is a history of intentional changes, who made each change, when and why they made it, and how it relates to the changes that came before. Git isn't a more sophisticated undo button or an automatic backup folder. A cloud storage service that synchronizes a folder, such as Dropbox or Google Drive, preserves the latest state of your files. Git preserves something different, a record of how you reached that state, one deliberate step at a time, with a human explanation attached to each step. That distinction matters as soon as two people modify the same file. The latest state wins, and here's what each of us intended, produce very different outcomes when those intentions conflict. Git exists because of a licensing dispute in 2005 involving BitKeeper, a tool the Linux kernel project had been using to manage contributions. When that arrangement fell apart, Linus Torvalds wrote the first version of Git in about 10 days. It's worth pausing to consider the engineering pressure behind it, coordinating a huge number of contributors, many of them editing overlapping parts of the same codebase at a scale where relying on a centralized server for every operation would be painfully slow. That's why Git is distributed, why creating a branch costs almost nothing, why its objects are protected by cryptographic hashes, and why it remains fast even at the scale of the Linux kernel. These weren't arbitrary design choices. They were direct responses to an extremely difficult coordination problem. Under the hood, Git has four main kinds of objects. A blob contains raw file content. Notably, it stores only the content, not even the file name. A tree is a directory listing that maps names to blobs or other trees. A commit combines a tree with references to its parent commit, or commits and metadata such as the author, timestamp, and message. Together, these form a complete snapshot. An annotated tag attaches a human-readable name and metadata to a specific object, usually a commit. Here's the detail that makes the rest of Git fall into place. Every object's ID is a hash of its content. Change a single bit in a file, and Git creates a new blob with a new ID. The old blob remains untouched. This should sound familiar because it's the same content addressing concept covered in Week 0's file system section, now applied to version history. It also means that a commit represents a full snapshot of your project at that moment, not merely a diff from the previous commit. Git calculates diffs for display because they're easier for humans to read. Internally, however, it reuses any blobs that haven't changed instead of duplicating them. That's why a Git repository doesn't balloon in size simply because you commit often. This content addressing model is also why Git has added support for SHA-256 repositories alongside its traditional SHA-1 format. SHA-1 has known weaknesses involving deliberately engineered collisions, and Git's entire object model relies on hashes identifying content reliably. Strengthening that foundation is therefore an integrity improvement, not a cosmetic one. Once you understand that Git objects are content addressed, a branch turns out to be little more than a movable reference to a commit. Head usually refers to a branch name, and that branch refers to a commit. Follow the parent references backward, and the history forms a directed graph rather than a straight line. A merge commit is simply a commit with more than one parent. Creating a new branch is nearly instantaneous because Git creates a new reference instead of copying your project. Git log -- graph draws that structure as ASCII art so you can see it. Eventually, you'll also encounter a state called detached head. This happens when head refers directly to a commit instead of a branch. You can explore freely in that state, but a new commit won't have a branch reference following it. That commit can therefore be difficult to find after you switch elsewhere. Before moving away, create a branch that points to your current commit. There are three distinct states to keep in mind while you work: the working tree, which is what's currently on disk, the index, also called the staging area, and head, which represents your current commit. Git status compares the working tree with the index and then compares the index with head, reporting the differences. Seen this way, git add is no longer a mysterious extra step. It lets you decide exactly which changes will go into the next commit, so you don't have to stage everything at once. Git add -p walks you through your changes one section at a time. It lets you stage some changes from a file while saving others for a separate commit. This is genuinely useful when you've been working on two things at once and want the history to reflect that clearly instead of combining everything in one messy commit. So what happens when two branches need to come back together? There are two main possibilities. If main hasn't changed since you branched from it, Git can perform a fast-forward merge. It simply moves the main reference to your latest commit. No new commit is needed because the histories never truly diverged. If both branches have advanced independently, Git performs a three-way merge. It finds their common ancestor and compares the changes on both branches with that commit. If you and your lab partner modified different files or different parts of the same file, Git can usually combine both sets of changes automatically and create a merge commit with two parents. If you both change the same lines, Git cannot determine which intent should prevail, and it reports a conflict. A conflict doesn't mean Git has failed. It means Git is being honest about its inability to reconcile two different intentions, so it shows you both versions and asks a human to decide. You'll see a section, head, followed by your version, a line of equal signs, the incoming version, and finally equals and finally and steini, with a branch name. To resolve the conflict, search for the eSection markers and decide what the merged result should contain. Then remove all the conflict markers, run git add on the file, and use git commit to finish the merge. Be careful not to commit files that still contain conflict markers. They may cause a build failure or, worse, silently alter the program's behavior. This happens more often than you might expect when someone resolves a conflict in a hurry. Rebase offers a different way to reconcile histories. Instead of creating a merge commit, it replays your commits one at a time on top of a new base, generating a new ID for each one. Remember that the ID is based on the object's content, including its parent reference. A different parent therefore produces a different commit object. The result is a clean, straight history that looks as though your branch never diverged. A merge, by contrast, preserves the more complicated but accurate history. The two lines of work separated and then came back together at a specific point. The golden rule is simple, but it's worth understanding rather than merely memorizing. Rebasing a branch that is still entirely local is generally safe because nobody else has based work on those commits. Once you've pushed a branch and someone else may have pulled it, rebasing rewrites commits they already have. Their local history will then refer to different commits from the upstream history, creating a confusing situation that may require careful reconciliation. Rewrite history before anyone else has seen it. Once it's shared, avoid rewriting it. That's the object model, the three working states, and the ways two lines of work can come back together. These three ideas let you reason about almost every Git command you'll ever run instead of simply memorizing it. Your lab exercise for this section includes a deliberately staged merge conflict. The goal isn't to avoid the conflict, but to resolve it cleanly. That covers one person's repository. Now let's put it on a server other people can reach. A remote is another copy of the history we just discussed, one that you can push commits to and fetch commits from. Here's an important distinction: Git itself is fully distributed. Every complete clone contains the repository's history, not merely a partial cache. GitHub isn't technically the original copy. It's a place your team agrees to use as a shared point of coordination, where everyone can exchange changes without emailing patches back and forth. Three commands perform three different operations, and confusing them is a common source of problems. Git fetch downloads a remote repository's history and updates your remote tracking branches without changing the work on your current branch. It's a safe way to see what has changed elsewhere. Git pull runs a fetch and then integrates the result into your current branch with either a merge or a rebase. It looks like one command, but it performs two distinct operations in sequence. That's why a pull can sometimes produce a merge commit you weren't expecting. Finally, git push sends the remote any local commits it doesn't have yet. Notice the remote URL when it starts with git at @github.com. That format uses an SSH connection. Each push is authenticated through the same key-based mechanism covered in the SSH section, the identity key you generated, and the key registration that GitHub manages on its side. It's no coincidence that both sections rely on the same trust model. The same solution is being reused for the same authentication problem. Once code reaches a shared remote, the question becomes, who decides whether it's safe to merge and how? That's what a pull request is for. It turns, should this be merged, from a decision made by one person into a discussion the team can have before the merge occurs. On a protected branch, direct pushes to main can be blocked entirely, even when someone is in a hurry. A required review means at least one other person must explicitly approve the change before it can be merged. Required status checks mean that your CI pipeline, including the build and tests, must actually pass. A code owner rule can require changes to specific paths in the repository to be approved by the people responsible for that part of the codebase. For example, a change to safety limit code shouldn't slip through with approval from someone who has never worked on it. What should a reviewer look for beyond whether the diff seems reasonable? Check whether tests cover the new behavior, rather than merely confirming that the existing tests still pass. Look for changes to files that the patch has no obvious reason to touch. A bug fix in one module that quietly modifies the CI configuration deserves a question. Also check whether the commit message explains the intent behind the change, the why as well as the what. 6 months from now, that message may be the only context anyone has. All of this relies on an assumption that once seemed reasonable, the person who wrote a diff has read and understood it because they typed it themselves. That assumption breaks down when a diff is generated by AI. The code in front of you may have been produced seconds ago, and the person who opened the pull request may not have reviewed all of it. This doesn't mean that AI-generated diffs are automatically worse. It means the review standard should be at least as strict as it is for human-written code, and often stricter, because you can no longer assume that someone has already thought carefully about every line. Here's a practical checklist for reviewing an AI-generated diff. First, does it actually run, or does it merely look plausible? Those aren't the same thing. Check boundary conditions carefully because generated code may handle the obvious case well while quietly mishandling edge cases. Review the error handling. Does the code fail clearly and safely, or does it swallow an exception and continue? Finally, check for unrelated configuration changes or new dependencies you didn't request. Those additions are easy to overlook in a large diff and easy to regret later. In this lab exercise, you'll open a pull request against a protected branch and take it through the required review process. Next, we'll look at curl and a different version of the question, how do I find out what's actually wrong? This section isn't really about memorizing curl flags. It's about developing a debugging mindset. When something that's supposed to respond doesn't, how do you find the cause instead of simply guessing and trying again? Your browser deliberately hides an enormous amount of machinery from you: DNS lookups, TCP handshakes, TLS negotiation, and redirect chains. These layers remain invisible while everything works, but any one of them can fail. Curl-b brings those layers back into view. It shows the IP address and port it connected to, the TLS handshake, every header sent and received, and the final status code. Before we go further, there's one caveat worth mentioning. ROS2 uses DDS rather than HTTP for its own communication layer, so you may not use curl very often in robotics-lowercase specific work. However, the underlying debugging discipline of thinking in layers and isolating the failed layer applies directly to DDS, gRPC, and almost any network system you'll encounter. It's worth learning properly here, where the tools are simple. When you run curl-b, its output follows a simple pattern. A line beginning with A describes curl's own actions, such as resolving a name, connecting to a server, or negotiating TLS. A line beginning with EE contains something curl sent to the server. A line beginning with E contains something the server sent back. Once you can recognize those three prefixes at a glance, a wall of verbose output becomes a timeline you can read from top to bottom. Start by breaking a URL into its components. This gives you a clear debugging order instead of a vague sense that it's broken. The URL https://api.example.com:8443/v1/robots?. ID equals 42 contains the scheme HTTPS, a host that DNS must resolve to an IP address, the port 8443, the path /v1/robots, and the query string ID equals 42. Each component can fail independently. Unless you separate them, it's not working. Tells you nothing about where to look first. Hostname resolution is where many debugging sessions should begin, but often don't. Get end hosts uses your system's configured name resolution process, which may consult /etc/hosts, DNS, and MDNS in a defined order. That's why it should be one of the first tools you use. Dig, by contrast, queries DNS more directly, and bypasses much of the system's normal resolution logic. The difference between the two can reveal a particularly frustrating class of bug. You might change a DNS record and see the new value immediately with dig, while the service still fails to find the new host because of a browser cache, a stale system resolved cache, or an unexpired DNS record. The reverse can also happen. Someone may have added an entry to /etc/hosts for local testing months ago and forgotten about it. That entry can silently override DNS until someone remembers to inspect the file. Get end shows the result your system will generally use, while dig shows what the queried DNS server says. When they disagree, that difference often reveals the cause of the problem. Three addresses are frequently confused, so let's be precise about each one. 127.0.0.1 is the IPv4 loopback address. It refers only to the current machine and isn't reachable from another one. Localhost is a host name that normally resolves to a loopback address, although it's still a name rather than an address itself. When a service binds to 0.0.0.0, it listens on every IPv4 network interface on that machine. As a destination for a client connection, however, 0.0.0.0 is generally the wrong choice because there is no specific remote host called everywhere. Docker containers add another important detail. A container's localhost refers to the container itself, while the host machine's localhost refers to the host. They are separate loopback interfaces that happen to use the same name. Trying to reach a host service through localhost from inside a container is therefore a common mistake. The client is pointing into the wrong network namespace. The service may be working perfectly. Binding a service to 0.0.0.0 also has security implications. During local testing, it may expose the service to your entire network rather than only to your own machine. That's easy to do accidentally when you're trying to get something working quickly. HTTP methods and status codes provide a shared vocabulary for a request and its outcome. Get retrieves a resource. Post submits data, often to create a resource or trigger an operation. Put and patch update an existing resource, while delete removes one. Status codes are grouped by their first digit. A 2xx code indicates success, and a 3xx code indicates redirection. A 4xx code means there is a problem with the client request, such as 404 not found or 401 unauthorized. A 5xx code indicates a problem on the server side, such as 500 internal server error or 503 service unavailable. Interpreting those codes in context matters more than memorizing a table. A 401 means the request lacks valid authentication credentials. A 403 means the server understood the request but refuses to authorize it. A 404 often indicates an incorrect path, but a misconfigured reverse proxy can also return it when it doesn't know where to route the request. Don't assume that every 404 is simply a typing mistake on the client. When you see a 5xx response, first check the server or service for a failure before investigating the client. The status code is already telling you where to begin. A handful of curl flags cover most everyday needs. -I requests headers only, which is useful for a quick check without downloading the response body. -v produces the verbose trace we just discussed. The -S combination is useful in scripts and CI jobs. The lowercase hides the progress meter so your logs remain readable, while the uppercase -S ensures that error messages are still displayed. And -X post -H content type application JSON-d sends data with an explicit HTTP method and content type. Before building an automated check around curl, remember that it doesn't return a non-zero exit status merely because it receives a 404 or 500 response. From curl's perspective, it successfully communicated with the server, even if the server's answer was an error. In a CI pipeline, a broken endpoint may therefore pass a poorly designed check. Add -fail or -fail with body when you want HTTP error responses to make the curl command fail. Sometimes curl isn't available, and that's when understanding HTTP as a protocol becomes especially useful. An HTTP version 1 request has a defined text format sent over a TCP connection, and you can enter it manually. Netcat w1.127.0.0.1 port opens a raw TCP connection. If you enter get/ready HTTP/1.1, a host header and connection, close, followed by a blank line, the server returns a real HTTP response. Netcat doesn't understand HTTP. It simply sends the bytes you give it through the TCP connection without interpreting them. You and the server are responsible for following the protocol's format. The blank line at the end isn't optional. It marks the end of the HTTP headers. Without it, the server may continue waiting because it doesn't know that you've finished sending them. This detail demonstrates what a protocol really is, an agreed-upon format that both sides follow, not magic. TLS adds another layer that you should be able to inspect directly. Open SSLS_client-connect host, port-server name host lets you examine a certificate manually. The -server name option sends server name indication, or SNI. This tells a server hosting multiple sites which certificate to present. If you omit it, the server may return a different certificate from the one you intended to inspect. A certificate verify failed error means that your machine cannot validate the certificate against its local trust store and the available certificate chain. The server may be misconfigured, or the certificate may genuinely be untrustworthy. Authentication tokens also deserve careful handling. A token isn't merely a password substitute, it's a scoped grant of permission. Store it in a proper secret manager, limit it to the narrowest scope required, and never put it in your shell history, a log file, or a commit. This isn't hypothetical caution. Automated scanners actively search public repositories for exposed tokens, which may be abused within minutes. GitHub's push protection detects many common token formats before a push completes, and tools such as Git secrets can catch others locally. At runtime, inject secrets through an appropriate secret management mechanism or environment variables, instead of writing them into files that might be committed accidentally. Once the connection works and you have a response body, JQ lets you inspect a JSON response by structure instead of squinting at one long line. It's a useful tool well beyond this course. The complete debugging sequence is now clear. Check the URL, then DNS, the IP address and TCP port, TLS, the HTTP status, and finally, the response body. The same layered reasoning applies to the Compose health checks we'll discuss later. Compose services discover one another by name through DNS, and a health check endpoint is usually an HTTP status check at the end of that same chain. One final distinction, curl and wget are designed for different jobs, even though people sometimes use them interchangeably. Curl is well suited to interacting with API endpoints using headers, methods, tokens, JSON bodies, and verbose debugging. wget is designed primarily for downloading files, such as a release archive or recursively retrieving a static site. wget-c resumes a partial download instead of starting over, while wget-r-np recursively downloads a directory tree without following links into its parent directory. The lab for this section is called Visual Relay. It asks you to apply this layered debugging approach to a failing service and discover the cause yourself. Now for the final piece, making the environment around your code reproducible on another machine.